Thanks very much. Is it on? I guess there's no need to shout. I'll shout if people fall asleep. So I should apologize. First of all, this is not really a school talk. This is really a research seminar. So what I would like you to do is, if you don't understand anything, please stop me, ask questions. Even if you think they're stupid, they're probably not stupid. They're probably quite profound. So what I would like to do is really discuss how you measure distances in cosmology. How do we measure distances in cosmology? And that's what essentially the basic idea of this talk. So the questions we want to try and address here, do we have a pointer? I feel a bit lost. Yeah. Oh, cheers, thanks very much. So first question, very, very basic question, is photon number conserved? Usually we assume that as photons travel through the universe, their number is fixed. Okay? But we can ask, is that actually true? Secondly, we can ask, is gravity really described by a metric theory? Okay? Einstein's general relativity is a metric theory of gravity. String theory, the description of gravity is through a metric. So this is a very basic assumption, and it would be nice if we could test it. Okay? And also the question, do photons travel on null geodesics? Okay? And then finally, the other question we want to ask is the universe really expanding in an accelerated way? We know it's expanding, but it appears that the universe is actually accelerating. Someone's stepping on the cosmic gas pedal. And the question is that really true? We want to know. Nazim? I don't care. So what I want to do is I want to see if I can test this hypothesis. So I'm going to come from it very much from the experimental point of view. I'm not going to necessarily put alternatives. There are alternatives like the modified Newtonian dynamics. I don't believe in it, but it's an example. Okay. So I'll start with I don't know what people have told you, but we currently, the general status quo is that we believe that the universe is accelerating. 1998, people realized that supernovae were dimmer than they would have been if the universe wasn't accelerating. Why is that? In a universe where the universe is accelerating, the supernova are carried away from us faster. And so they're actually further away. And so, of course, they appear dimmer than they would if the universe was not accelerating. If we look at this cosmic microwave background and clusters of galaxies, these imply that most of the energy in the universe does not cluster. It's not of the form of a table, of a planet, of a galaxy. Most of it is smooth. And then, finally, most recently, we can look for correlations between the cosmic microwave background and large-scale structure. And I'll say a little bit about this. So here's the WMAP data, a recent satellite. The cosmic microwave background. Blue is cold, red is hot. And we can split this into two parts. The first part was formed when the universe was only 100,000 years old. Okay? So it was formed at a redshift of 1,000, and it looks like this. And the second part is a so-called integrated Sachs-Wolf effect, which occurs at very low redshifts, a redshift of 1 or 2. And you can see it looks very different. And the point about this is due to the universe accelerating. If the universe doesn't accelerate, there's nothing in this map. This map would be just uniform. Okay? So the question is, can we search for this part that has been produced very recently? And the way you can do that is by looking for correlations between this map and maps of the large-scale structure of the universe, distribution of galaxies, or what has been done is to look at X-rays. X-rays, yes?
A simple argument why the monospatial frequencies are discriminated against if there isn't such an acceleration.
It's just a very simple thing about the general relativity that in a flat universe where the universe is not accelerating, the gravitational potential, phi, is a constant on large scales. And essentially this delta T temperature difference is proportional to phi dot. So when the universe begins to accelerate, phi begins to decay. And so you pick up this term. So you can look for this cross-correlation, and people have found it. So here's the correlated part of the X-ray map. Here's the WMAP data. if you look really hard, you can see some correlation. That's why it's only 2.5 sigma, because it's actually really hard to see. So I've smoothed the X-ray map, and you can sort of see a little bit of a blue spot and a blue spot, a kind of a red spot. Okay, it's 2.5 sigma. That's why particle physicists like 5 sigma. But it's the first direct evidence of the evolution of the perturbations for dark or for acceleration. Let me go back to supernova, though. The real evidence comes from supernovae. For those of you who don't know, supernovae are very bright explosions. Here's a host galaxy, the fuzzy one, and here's a supernova. And you can see at maximum, it actually outshines the host galaxy. And you can see here's one here. So what we're saying is that these supernovae actually appear dimmer than they would if the universe was not accelerating. The question, of course, is how do you know how bright they really are? Okay, so that's a fundamental thing. What is the intrinsic luminosity of the supernova? And they use a very clever technique called the MLCS method, multi-light curve synthesis, and it's an observed correlation. Brighter supernovae take longer to become dim than less bright supernovae. So the brighter the supernova, the longer it stays bright. And this correlation allows you to calibrate for the intrinsic luminosity of the supernova, which is a key problem. And if you use this technique, you can get the brightness, the intrinsic, well, the magnitude, the brightness of the supernova against redshift. Okay, and have a look at this bottom one. Here I've plotted. There are 3 curves. This bottom curve corresponds to a non-accelerating universe. This one corresponds to an accelerating flat universe, and this one corresponds to an open universe. And you can see the majority of the points lie well above this non-accelerating universe. I think, well, you can just you can look at it by eye, or you can go and do the statistics, and the statistics give you this plot. Here we've plotted lambda, the amount of dark cosmological constant. Here's the amount of matter in the universe. And these are the confidence curves. How confident are you that the universe has a certain set of parameters, omega matter, omega lambda? And you can see that the best fit is around here, with a lambda about 70% of the energy density in the universe, and about 30% in matter, probably matter. This corresponds to the flat universe, this line. And that's useful because it actually corresponds very similar, or you can't really see this, to what we find from other data. The cosmic micro background prefers this line. The supernova prefers this line, and they intersect over here exactly where clusters prefer. That's why it's called the concordance model, because everything, at least naively, agrees very well. So the concordance model, which people tend to believe in, is that the universe is roughly flat with about 70% of the energy in the form of some dark energy.
Which was the cosmic background?
This one, sorry. You can't actually see it, but cosmic micro background prefers flatness. And then you have this and this. So they're nicely orthogonal. Okay. But acceleration is a really profound problem at every level. Okay? Acceleration is caused by a cosmological constant, but the cosmological constant that we're talking about when we say lambda over here, it's 120 orders of magnitude smaller than the naive particle physics estimate. So it's about 10 to the minus 120 times the Planck mass to the 4th. So lambda. So this is your naive estimate of the cosmological constant, and the observed one is 120 orders of magnitude. It's probably the worst estimate in physics. It has to be the worst estimate. So it's extremely difficult to understand the origin of this. But it's even worse. If lambda was exactly 0, that would actually be easier to understand than having a very small cosmological constant. Because if it was 0, it could be protected by some symmetry. Say, it can't be there because of some symmetry. Okay? even worse, in my view, is the coincidence problem. For such a small value of lambda, the universe has only just begun to accelerate. Like yesterday. Well, not yesterday. A billion years ago. Okay, but in cosmic times, just yesterday. So then you have to ask, why are we living at such a special time? You know, if we were here 2 billion years ago, the universe wouldn't have been accelerating. So why are we here at such a special time? So at the moment, we are violating the Copernican principle in time, so why not in space? The Copernican principle says that we do not occupy a special place in the universe. Well, if we're going to violate it in time, why not in space? And if we allow ourselves to violate in space, we can have lambda equal to 0. So it means that this problem goes away. We can just invoke some symmetry. So it's a very interesting problem, a very profound one. Yes? Yeah. Right.
Then inflation is in the future at least, eternal.
Right.
There's always some patch that always inflates.
Right.
So why can we not live in a patch that's already undergone its inflation and just normally expanding, and suddenly we intersect with a patch that is inflating? So now when we make our measurements today, we see an inflating universe. We see something that's expanding, that's accelerating. But you probably see some dipole effect in that.
So so you're thinking of something. So if this is space, over here lambda is 0, and over here lambda is bigger than 0. Yeah, that's essentially, you need spherical symmetry, otherwise this would cause very large anisotropies in the CMB. So there would actually have to be, over here, lambda greater than 0, would have to be a spherical region, it would be spherically symmetric, yeah. But then we're at the center of our observable universe. So why? So that's why the Copernican principle becomes important. Yeah. So yeah.
As long as one remembers that it's possible that is the case.
Yes, absolutely. It's possible that this is true. And so which do you prefer? Do you prefer lambda to be very small and hard to explain and violate the temporal part of the Copernican principle? Or do you prefer to violate the spatial part and have lambda 0? Okay, so this is philosophy. Sorry? Oh, absolutely. That's what we would hope, yeah. You could always, of course, invoke the anthropic principle. It couldn't be larger. Yeah. So, one of the nice alternatives is that the universe is not accelerating. Okay? So, Saki, Turning, and Caliper suggested that maybe the supernovae are dimmer, not because they're further away, but because some of the photons are getting lost on the way. They're kind of lost sheep who get lost. And their mechanism was quite clever. They suggested coupling photons, electromagnetism, to an axion. Now, axion is a hypothetical, it's not a real, well, it's never been discovered, but it's a hypothetical scalar field, okay? And in the intergalactic cosmic magnetic field, what would happen is that photons would change into axions. And we can't detect axions. So they would be lost. They would change their shape, effectively, and be lost. Okay? And if this is correct, the universe would not be accelerating. It would just be that we were losing photons. Okay? The advantage is there would be no coincidence problem. No coincidence problem would be necessary because the universe wouldn't be accelerating. Okay, so... Oh, yes, you can do it self-consistently. It's very similar to neutrino mixing, where neutrinos mix in flavor mixing. So what you have is eigenstates. You have a photon eigenstate and an axion eigenstate, and then they mix through this coupling. So it doesn't violate photon energy conservation.
It's important enough, or if you can actually see it on those scales, can you see it in your universe, or would that change all our calculations?
So they, Saki et al., have tried to calculate everything, and they've shown that it's compatible with everything except what I'm going to show you. So well, theirs is 2 years ago. So it's but I think it's a very interesting model for scenarios in which the universe is not accelerating, and so you don't have this coincidence problem. Okay. So a simple view of this axiom mode, you have a source like a supernova. It emits mainly photons, but after a certain distance, which is set by the strength of the intergalactic medium, the mass scale of the axion, etc., you lose some of your photons into axions. And on average, there's one axion polarization state, 2 photon polarization states. So on average, you lose 1/3 of your photons. And that provides an excellent fit to the supernova data, actually. That's what Saki et al. Showed, is that with a non-accelerating universe, you lose 1/3 of your photons and you fit the data very well. So they were like, hey, we actually don't need acceleration. So there's some other exotic possibilities that we can also test, and I'll show you why. One of the possibilities is space-time torsion. I won't say anything about this. Non-metric aspects to gravity, modified Newtonian dynamics. You basically say that Newton's law of motion is not F equals ma, but you have corrections. And you use these corrections to mimic the effects of dark matter. So in MOND, you don't have dark matter. You could give the photon a mass. You could couple the photon to other fields. Or there could just be some absorption or emission of photons. Okay? So all of these issues, these things, I want to try and test, along with axion-photon mixing. So that's where the reciprocity relation comes in. It's now 70 years old. And what does the reciprocity relation do? It links 2 distances. Okay? We have the luminosity distance, how bright something is, and the size, the angular diameter distance, d sub a and d sub l, and the reciprocity relation links them via this factor of 1 plus z squared. Okay? And the key thing about this is that it's valid in any metric of theory of gravity if photons travel on null geodesics and their number is conserved. Okay? Right. It is on a practical, So there's a geometric theorem which doesn't require photon number conservation, but when you apply it in astronomy, you have to assume photon conservation. So, just to remind you, luminosity distance, we have some bright object, and then as it gets further away, as distance increases, it gets dimmer and dimmer. Okay? So we can estimate the distance like that, and that's the luminosity distance. And then we have angular diameter distance. We have a standard rod of a certain length, and as it gets further away, the angle that it subtends gets smaller. And the reciprocity relation says that these 2 distances are linked by this formula. In other words, they're equivalent. You only need one of them, and you have all the information. And that's what we want to test. So technical, now I'll get on to details. We have supernova data to test the luminosity distance, and we have 4 data sets for angular diameter distance. Radio galaxies, we have 2 hotspots, and we can see how far apart they are. Ultra-compact radio sources, and X-ray cluster estimates using Sunyaev-Seldovich effect. I won't go into the details of how they estimate this, because it's very tricky, and a lot of people don't really believe this. Okay, it's very tricky business. Okay, but anyway. Let me show you some of that, the ultra-compact radio sources. This is the angular size in milliarc seconds against redshift, and here are the points. Bind points to reduce the error bars. And here's the prediction of a flat, non-accelerating universe. And here's the prediction of an accelerating universe. And you can, I think, convince yourself that the accelerating universe is a better fit than... In fact, you can show that the non-accelerating universe is ruled out at 95% confidence from this data set alone. The key point is axion-photon mixing would not affect the angular diameter distance. Axion-photon mixing would violate the reciprocity relation. So that's the key thing. We can do similar things. This is not such good data. This is the Rees et al. X-ray data. But we can use that as well. The large error bars don't weight it very highly, but Okay, I'll skip over this. Basically, if we look at the photons interacting with some other field or with electrons or any other source, we can parameterize it by the Boltzmann equation with some non-trivial scattering term that scales with redshift in some way. We can integrate that. I won't bother with that. So let's consider the case where we consider something like Compton scattering of free electrons. Then the reciprocity relation, the left-hand side here was the normal reciprocity relation. Now it becomes modified by this exponential term. And here, E is the Hubble expansion, essentially. And gamma is some scattering cross-section coefficient, interaction cross-section. And we want to say, what does the data say about gamma? Gamma equal to 0 would be the reciprocity relation. So what does the data say? Oh, just a naive thing. If you go and calculate for current estimates of the number of free electrons in the intergalactic medium, you predict that gamma should be about 0.001. Okay? Just, we know the intergalactic medium is ionized. And this is what we find. Okay. So let me explain it a bit. Here's gamma. Here's omega k, the curvature of the universe. So a flat universe corresponds to here. The reciprocity relation corresponds to this line. Okay. The blue contours are what you would get from just using the supernovae alone. So you get basically nothing. This outer one tells you the 95% confidence. But when you include the angular diameter distance data, you shrink down to this tiny little region, well, small region, and the best fit is there, corresponding to negative gamma, which corresponds to the fact that the supernovae are brightened relative to the angular diameter distance. Very, very strange, needless to say. Now, if axiom photon mixing were correct, this should be up here somewhere. Not only is it not up here, it's actually down there. It's violating the reciprocity relation at 2 sigma. And that's very surprising. You can show the same thing with omega lambda, the energy density in vacuum, and you see the same thing. It's really the same curve. Okay, so why is this? Okay, here I plotted redshift on the bottom and the effective magnitude on the vertical scale. How bright are the objects? And the blue, well, this is really distance, let me say that. The blue is the angular diameter distance data. So using sizes. Red is the supernova data using brightnesses. How bright is the object? And you can see up until about here, they agree quite well. But after this, they start to disagree. Okay? And so here's the best fit to the blue data. And then here's the best fit with some gamma equals 0.06. The same underlying geometry, and you get this curve. Okay? So that's the origin of this effect. The supernovae are brighter, in other words, further down, than the reciprocity would like them. The reciprocity relation would like them all to line up. Okay. So that's the origin of the effect. Remember, axiom photon mixing make the supernova dimmer. So it's giving we've got the opposite effect, and it's predicted. So the game comes down to now trying to say, well, why? Why is this? You know? Why don't they lie on top of each other? Let me just say a bit about axiom photon mixing. Essentially, it's ruled out as an alternative to acceleration because they predict that the supernova should be dimmer, not brighter. And here's a curve. I won't go through it. The key idea with this is that axiom photon mixing affects the supernovae, but not the angular diameter distance. It doesn't change the size of the object. It just makes them dimmer. So it violates the reciprocity relation. So, yeah. The axiom. Scalar, I think I did this while you were out. Yeah. we can say, well, maybe it's not photons being lost. Maybe it's something more profound, and so we can widen it to allow our source that's causing the interactions with the photons to evolve differently from just co-moving number density being conserved. And we can just throw in a parameterization here, a beta, which would parameterize our ignorance, really. So, yeah. Sorry? That's a good question. To be honest, there is a degeneracy in this parameters, because near alpha is, I'll show you. When you look at what happens, you get this plot. So, again, the reciprocity relation is this yellowy green line here. And the red is the 95% confidence interval. And you can see, again, it doesn't intersect the green line. Okay. The plots that I showed you before assumed that alpha was -2. So it was here. If you allow for your scattering objects or interactions to scale differently, you can get various solutions. And of course, there is a degeneracy. You can see a kind of hyperbolic degeneracy here, exactly with the fact that you don't need, in a sense, there's a degeneracy between the three parameters. But, yeah.
Is there, yeah. Is there any way, so these are you're empirically changing.
Yeah, this is just parameterizing possible deviations.
Right. Is there any way you can sort of motivate this from a theoretical point of view?
Yeah, so this part is just a Boltzmann equation. You assume that the photons are being lost or gained through scattering with some object whose number density scales depending on alpha. So if you put alpha equals to -2, you're saying that they are scattering from objects whose number density is constant. It's just, okay? When alpha is less than, is bigger than 1, oops. When alpha is bigger than 1, what you're saying is that the number of photons, the number of objects that you're scattering off, is actually increasing with time. Very, very strange. So you either live with up here, where gamma is negative, or you live down here, where alpha is bigger than 1. It's extremely strange. So beta, of course, well, it's encapsulated in this rotated parameter. So you could, of course, choose beta to be very different from 1. But then you have no theoretical prediction. I mean, I can't give you a motivation for this. This is just saying, let's consider power law deviations. If you calculated torsion or Mond or something, you could make some predictions for this, presumably. So that's the next step. So there may be a much better way to parameterize the deviations. I'm happy with that idea. But I think the basic the basic result is robust. So what's the boring or probable explanation? The probable explanation is just bias or systematic error. We use data sets. They say our error bars are this big, but they're actually this big. So that's probably it. Or it could be more subtle. It could be gravitational lensing. Right? Now, it can't be naive gravitational lensing because the reciprocity relation allows for lensing. It's true even when there's lensing. But we are comparing very different sources. We're comparing supernovae with radio bridges. And so we're considering different angular scales. And so lensing effects may come in through a kind of averaging. The one is averaged, the other one's not. But it's very non-trivial to understand. Could be Malmquist bias. In other words, we preferentially see bright supernovae because the dim ones are too far away to see. Whereas the radio galaxies, we see them basically irrespective of whether they're bright or not. Okay. Or it could be K-correction effects. It could be subtle. The fact is, supernovae that we're looking at are mainly in the visible or infrared, whereas the radio galaxies are, of course, in radio. So we're looking at different frequencies. So there could be something. Okay, I won't bore you with more systematics. But what I think is the most exciting thing, and I think we'll hear more and more about it over the next few years, is the future, okay, for distance tests. So, luminosity distance, we have the Joint Dark Energy Mission, which So it's this NASA Department of Energy mission. SNAP is the leading candidate for satellite telescope to measure supernovae. And we'll get thousands of supernovae, maybe 2,000, out to high redshift. So it will give us the luminosity distance accurate to a few percent. And just for those of you, that's what it looks like. The SNAP proposal for the telescope. The angular diameter distance is the key one, because we don't really believe the error bars at the moment, to be honest. And the key is the planned, in progress, just a recent call for proposals, is for large galaxy surveys to go beyond the Sloan Sky Survey, out to a redshift of about 3. And then we can do something very clever. We can use the Baryon oscillations imprinted at decoupling as a standard ruler. Okay? Completely linear physics, nothing complicated, and we can follow the evolution of the Baryon oscillation, the wavelength, as a function of redshift, and use that to get a standard ruler as a function of redshift. And here is the simulations for such a survey going out to a redshift of 3. And here are the predictions of what we can get on the oscillations. So these oscillations come from the fact that in the early universe, photons were coupled to the matter and they were oscillating. And so they imprint a characteristic sound wave essentially on it. But this sound wave is being stretched by the expansion of the universe. And if we can follow it as a function of redshift, we've got a perfect standard ruler. And as a result, here are the error bars on the angular diameter distance as a function of redshift, and they can be down at 2 to 4 to 5%. And that's a revolution. Because the error bars I was quoting are huge, even out to a redshift of 1. So I think there's going to be a revolution in cosmology in the next 10 years. Very exciting thing. And this will mean that we will be able to test the reciprocity relation by at least an order of magnitude. Instead of having a 2 sigma detection of a violation, we'd have a 5, 6, 7 sigma detection. So I think the reciprocity relation will become a powerful test of very fundamental physics. Doesn't depend on cosmology, doesn't depend on dark energy dynamics. Just tests very fundamental physics. So that's kind of exciting for me. So conclude, don't want to bore you too much. Well, too much more. Okay. The reciprocity relation is violated 2 sigma. That's our basic result. Okay. Probably it, at the moment, accounts for systematics that people haven't known about, but this is a useful way to uncover that systematics. But it could be something exotic. For example, if Newton's constant were larger in the past, it would have dimmed supernovae. It would have made supernova brighter, okay? And so this could explain the fact that supernovae appear brighter than they should. For example, just as an example of what it could be. I don't believe it. But then our main result, in terms of current theories, axiom photon mixing, you could say strongly constrained, probably ruled out, essentially, and it's not an alternative to acceleration. It's kind of a pity because I like that theory very much, but it is what it is. And the future, the next 10 years, with chaos and the SNAP satellite, looks very good for testing exotic physics. I'll stop there. Thank you. Yes. Yes. So, yeah. If Z equals H over H naught. What? Oh, so yes, I should probably be as clear as possible. The reciprocity relation works for any geometry. We are, of course, assuming a Robertson-Walker background, yes. Yes, effectively, I mean, so that's a very good question. Since the reciprocity relation is valid in all geometries, you can't use it to test Robertson-Walker. So the fact that we see a deviation, I see what you mean. Okay. We are assuming Robertson-Walker background. Yeah, I understand what you're meaning. No. I thought, you're thinking, because we're using a Robertson-Walker E of Z, the fact that we then get an inconsistency might be a reflection of assuming Robertson-Walker. But I think it wouldn't work, because I think they should still lie on top of each other. You would just get something different from reality. But the fact that these are split cannot be explained, because we calculate both of them using this E of Z. So, yeah, it doesn't, unfortunately.
What about some weird thing like redshifts aren't quite what you think they are? They have some contamination.
Let me think.
But to put another twist on that, people from time to time write about the good old tired light theory.
Right. Essentially, this wouldn't explain. You can rule this out. I mean, that's another way to put this. We could rule out the tired light theory that way.
But that's what you ruled out is absorption theory. What about a color change theory?
So it could be that what's happening is, actually, I don't quite, so what you would need is that the supernova would be emitting, say, in ultraviolet, and then some of those photons get converted down strangely, into visible, but the visible is unaffected, so that the supernova appear brighter because of that. So if you can concoct a theory like that, that would be very
Here's a off-the-wall proposal. We made it up. Okay, it could be complete nonsense. Suppose it's the case that in space, the crystal distribution now is highly homogeneous.
right.
As a consequence, there's gravitational, dynamical friction in the photons, and therefore we're losing some of their wavelength. I mean, we have to calculate to find out whether it's true. Probably it's nonsense.
So are we losing or gaining photons? Because this is saying we're gaining.
Any photons, you're losing some of the wavelength. You're making them longer wavelength.
Oh, you're making them shorter wavelength, longer wavelength.
You're converting them down.
But so what will happen is that because we're observing at a given frequency, we will lose those photons from the detector.
From that frequency, but we'll see them in the lower frequency.
Well, of course, what with these, we have to ask what these people did with these supernova, and so they look in specific bands, and so they wouldn't pick up those lower frequency photons. So they would expect that from that, you would expect photons to be up, the supernova to be up here, dimmer. Okay, but they're actually brighter. That's the problem. The supernova are brighter than they should be. That's the crazy thing about this. The supernova are dimmer, or brighter. The nice thing is that this deviation grows exponentially. So if we can get more data out here, the statistics will rapidly improve. So one alternative is people gave the supernova people a lot of criticism, say it could just be dust. Dust is absorbing the photons. This proves that it can't be, because if there were dust, again, the supernova would be up here, brighter, dimmer than the angular diameter distance. So if these points were just inverted, it would be nice. You'd say, you would need a laser sector. You have sorry? Dynamical friction.
Right, dynamical friction, just like stars going through a cluster. Photons going through a cluster of galaxies.
Yeah, I guess, I don't have a good intuition for that. It would be, yeah. I mean, the question would be, wouldn't you lose as many photons as you gain, sort of thing?
I don't know. It's funny, this source.
Make it energy dependent, but perfect.
Or, you could make a supernova very bright at ultraviolet wavelengths.
Of course, it is energy dependent. It's essentially equivalent to mass. You work out the standard dynamic friction.
Okay.
Sorry for wasting.
No, it's good. Hadn't thought of that. That was a...
Anything else?
Well, if we're going to go wild, we could assume that h bar varies with distance.
So that's a good question. Does the reciprocity relation hold if fundamental constants vary? That I don't know.
Well, it depends. I mean, I don't think it would depend on h bar, right? Because it's not telling
No, I mean, well, if h bar increases, then your photons are getting higher frequency, but well, I don't know how that converts to apparent.
What Bruce is calling reciprocity is mixing up two things. There's a purely geometrical thing.
Right.
And then you are then folding in with that the way that luminosity depends on the upcoming distance. And actually it would be clearer if you separated those out.
Right, yeah.
The purely geometrical thing depends on whether light is moving on null duties
Right.
or not. That's it.
Right.
Nothing else in it. And then how that upcoming distance relates to luminosity now depends on all the other things we're talking about, photon energies and losing photons and so on.
But we can't measure that upcoming distance in any other way, right?
Yeah.
Okay. So it's a good question. There's an unsolved problem is how do you distinguish between photon number violation and deviations of gravity from a metric theory? That's an unsolved problem. We don't know how to look. How do you say, it's okay, it's just photons doing stupid things? Or how do you say, we actually have a deviation from a metric theory of gravity? That's an unsolved problem. Yeah. With the cosmic micro background. There's not very much overlap, I don't think. So these are measurements in the background cosmology, so the background geometry, whereas the micro background is sensitive to the fluctuations of the geometry, so capital phi. So at the moment, these don't depend on phi. So I think there's not a problem or not much you can do to correlate this data with the cosmic micro background. Oh, okay, wait a minute. You could try and say, well, if the supernova are being brightened because the number of photons is increasing or they're getting to higher frequency, we could look for that in the CMB. And we don't see that. The CMB spectrum is perfect black body. So you would have to make this effect very frequency dependent. But this is in the visible wavelength. CMB is in the microwave, so it's quite a long way. But certainly the axiom photon mixing people had to fine-tune their parameters so they didn't affect the cosmic micro background and did affect supernovae. So yeah, it's a good question. Yeah, very good question.
Is it the case that you expect any given supernova to shine in pretty much the same way as all the others?
This is a horrible question. So supernova theory is a complete mess, and these are type 1a supernovae. No one understands them. All we have is this observed correlation that if the supernova is brighter, so this is time, and this is the magnitude. So if a supernova is very bright, it takes a long time to become dim. If it's not so bright, then it gets dim very quickly. Okay? So this is an observed correlation. And when they first discovered this, all the models predicted exactly the opposite. They predicted the bright ones should decay very fast. So they don't understand what supernova are. We can't get supernova to explode in the computer. They kind of collapse and then just kind of don't explode.
So, I mean, is it conceivable that it is the case that if we had a full understanding of supernovae, then still would be all bright?
Yeah, it could be just evolution of supernovae. Yeah, absolutely. So, absolutely. The naive models that people propose, again, of supernova evolution, again, would make them dimmer, not brighter in the past. So, again, the obvious kind of things go the opposite way. So that's what's kind of intriguing about this. As I say, if these have been swapped around, you could just hand wave 10 different explanations. The fact that it's this way around, it's a little bit tricky. Another thing I'd like to point out is you might just say, the supernova, we trust them. The supernovae, they've been studied a lot. We trust them. This angular diameter distance data is rubbish. We don't believe it. They don't know how to measure the standard ruler. Okay? But the problem is, this data, the angular diameter distance data, agrees with clusters and the CMB better than the supernova data does. People are now arguing that this supernova data is evidence for evolution of the cosmic equation of state. They're saying, because this is what you should get, and we see this, it means, suddenly the dark energy started to evolve. Okay? So that's a nice thing about this, is you can say, well, actually, I don't think so. I think that it's the reciprocity relation. So that's the thing. It's the angular diameter distance data, which is the thing you probably don't trust as much as the supernovae, which agrees with the CMB and the clusters. And it's the supernova that doesn't now. So it's a nice little... But as I say, fortunately, statistics will improve rapidly. There's a lot of work going on in getting supernova between 1 and 2, so we'll get a lot more. And you can see, if we can halve the error bar on this is one supernova. If we can halve the error bar, it'll go from being a 2 sigma effect to being a 4 sigma effect. And suddenly that would be a much more serious thing. Much more serious statistics. I don't know if you know how to just crudely estimate. If you just calculate that, a 2 sigma would bring you compatible with that point. And that's probably, with this one again, it's probably 2 sigma. So it's something that in a couple of years you'll hopefully be 3 or 4 sigma, or it might go away. Who knows? I mean, I think the basic point is that it's actually a very nice way to test very fundamental things that we take for granted in cosmology. So, I mean, it's crazy that it's 70 years ago that we knew about this. This is nothing new in the reciprocity relation. But data in cosmology has been so bad for so long that, doing this was never a possibility until now. So it's exciting times to be around.